Welcome back, everybody. It's my great pleasure to introduce the next speaker, Csaba Schneider from the Federal University of Minas Gerais. Csaba originally is from Hungarian, and he holds a PhD from the Australian National University at Canberra, and she's currently working, as I said, at the Federal University of Minas Gerais. So please, now I don't see Csaba in evidence here. Okay, now it's...
Thank you.
Yeah, so it's, please, over to you, Csaba, when you're ready.
Can you hear me?
Yeah, we can hear well.
And can you see my screen?
Yeah, we can see it.
Okay, so thank you very much for introducing me, and thank you very much for inviting me to this nice session. And so I'd like to talk about these diagonal groups and diagonal structures. And this is joint work with Rosemary Bailey, Peter Cameron, and Cheryl Prager. And so I will present some work, and whenever I don't give any attribution to the origin of certain results, so these results make part of this joint work, which is currently under publication in the transactions of the AMS. It's already available on the website. So this is the main reference of this talk. So whenever I don't say where a certain result comes from, it comes from this paper. And this is joint with these collaborators. So I apologize, the rest of my slides are going to be handwritten, except for a couple of basic keywords. So let's start with the definition of the diagonal graph. So the diagonal graph can be defined using a Hamming graph. So in fact, we are going to start with the definition of the Hamming graph. So the Hamming graph, we take a set delta. So delta is a set and k is a number, which is going to be at least 1. In this case, it's going to be at least 1. And we will construct this Hamming graph, which we are going to call hk plus 1 delta. So you will see why k plus 1, but in this context, we are going to take k plus 1. So this is hk plus 1 delta. So the vertex set of this Hamming graph is the Cartesian product of delta, k plus 1 copies of delta, delta to the k plus 1. And the edge set is defined this way. So if you have two vertices, so I will label these vertices like this, like I will write one vertex delta 0 up to delta k. So this is an element of delta k plus 1. So I will start the indexing by 0 and I go up to k. So whenever I have two such vertices, these will be connected by an edge, or they will be adjacent in the graph whenever these are equal for precisely k indices. So all these entries are equal except for one entry, and that entry has to be different. So we are not allowing loops. So this is the Hamming graph. This is well known. It's used, for instance, it has applications in the theory of error correcting codes, because essentially in the Hamming graph, you link two vertices whenever the Hamming distance between is 1. So this is a well-known graph, and the distance in the Hamming graph corresponds to the Hamming distance between code words. So this is a very well-known and well-used graph. So why are we interested in the Hamming graph? Because of its automorphism group. It's easy to show. So this theorem is not our theorem. This is a well-known theorem that the automorphism group of the Hamming graph is the wreath product of two symmetric groups. So you can take the symmetric group on delta, and you can take the symmetric group of degree k plus 1, and the automorphism group is going to be the wreath product of these groups acting, like it's called the product action. So the base group is acting on the coordinates. Each individual factor of the base group is acting on a certain coordinate, and this sk plus 1 is permuting the entries. And it's interesting, this graph, and this group is particularly interesting whenever delta is finite, because when delta is finite and it has size cardinality at least 5, and the number k is at least 1, then the automorphism group of this Hamming graph, the automorphism group is in fact a maximal subgroup. So this automorphism group is going to be a maximal subgroup of the symmetric group, or possibly the alternating group. So even if you take symmetric groups here, the least product can be a subgroup of the alternating group. So maximal subgroups of a given group are always interesting to study, and this is one example of such a maximal subgroup of symmetric and alternating groups. So this is the Hamming graph, and I promised that I would talk about the diagonal graph. So to introduce the diagonal graph, let us suppose now that G is a group. So we are going to consider the Hamming graph hk plus 1 in such a way that our set delta, I mean, in the previous construction of the Hamming graph, we had a set delta. So now this set delta is going to be the underlying set of a group, right? And so to construct the diagonal graph, what we do is that first we introduce an equivalence relation on the vertex set of the Hamming graph. So we consider two vertices. So now two vertices have this form. So G0 up to GK, H0 up to HK, and these are elements of the group, right? And we call such vertices equivalent whenever the second vertex can be obtained by the first vertex by simultaneously multiplying each entry with the same element from the group. So here you see we are using already in the definition of this equivalence relation that the underlying set of the Hamming graph is a group. So we are using the group product to introduce this equivalence relation. And so we will use this notation. So we will put in brackets. So we use brackets G0 up to GK to denote the equivalence class of this entry of this of this vertex G0 up to GK. So notice that you can always multiply. You can always find the right sort of group element to make sure that the first entry is equal to 1. So this is the equivalence class can always be written. So if I have the equivalence class of this G0, G1 up to GK, so this is the same as the equivalence class of the identity G0 inverse G1 up to G0 inverse GK, right? So I can always write every equivalence class in this form, and this is like a unique representation of the equivalence classes. And now the diagonal graph. So what the diagonal graph is? So the diagonal graph, which we are going to denote by this gamma GK. So this is going to be the notation for this diagonal graph. So we sort of we started with k plus 1 in the Hamming graph, but we will we put k here. Hopefully it's not going to cause any confusion. So the diagonal graph is going to be the set of vertices. Is going to be the set of equivalence classes under this equivalence relation, which I have just defined. And as I said, so set of equivalence classes, so they can be written this way. So I can write, so G0 up to GK, so the equivalence class of this vertex, I can write it as starting with the identity and then G0 inverse G1, G0 inverse GK. And so these are the vertices, and two such vertices are going to be adjacent if and only if there is some vertex in the equivalence class of the first vertex. I mean, the elements of the equivalence class of the vertex are going to be vertices in the Hamming graph. So if there is an element in the equivalence class of the first vertex, then there is an element in the equivalence class of the second vertex, which are adjacent in the Hamming graph. So these would have to be adjacent in the Hamming graph H k plus 1, comma G. So this is all well defined. And so this is going to define a graph. So this is a symmetric, undirected graph. This is a regular graph. This is going to be a simple graph without loops. So it defines a graph. And here, the underlying set G, on the underlying group here, G can be finite or infinite. So this construction works equally well for finite and infinite groups. So another way of looking at this diagonal graph is written here. So now, so this is sort of equivalent definition of the same graph. So I'm now going to look at vertices like k tuples. I identify this vertex. So as I said, so every vertex, every equivalent class can be identified with a unique k tuple, assuming that the first entry is equal to 1. So in the second definition of the graph, I identify vertices with k tuples. And I put an edge between two k tuples if and only if these two k tuples are equal in precisely k minus 1 indices. That is, they are adjacent in the Hamming graph hk comma g. So this is one way of putting an edge between two k tuples. Or I can also put an edge between two k tuples if the second k tuple can be obtained from the first by simultaneously multiplying the entries by some group element. So this is the second condition. So here we get like edges of different types. So maybe later it's going to be important to be able to talk about it. That here, so the first adjacency condition gives me the edges that we call. Sorry, write it here. So the first adjacency condition will give me the edges that we call of type 1 up to k. So type 1 edge would be an edge such that the entries in the first position differ, but the entries in the other positions are equal. And the type 2 edge would be something where the entries in the second position differ and the entries in the other position are equal. And this is this other type, this second condition for adjacency. So this gives us edges of type 0. So this is what we call edges of type 0. So these are the edges of type 0. So this is gonna be somewhat, so I'm gonna refer to this later. Okay, so this is the diagonal graph. And now the diagonal group. So I promised diagonal graph and diagonal group. So I told you what the diagonal graph is. So let me tell you what the diagonal group is. So the diagonal group is a permutation group. So in order to define the diagonal group, you have to start already with a group G. So suppose G is a group. It can be finite or infinite. At this stage, it doesn't really matter. And you have to choose a number, k, at least 2, natural number. And now we set a set. As I said, it's going to be a permutation group. So we need to say first on what set it's going to be acting. So its underlying set is going to be the set G to the k. And now we have to sort of have to say what the group would be generated by. So we will list a bunch of permutations, and we'll say that this diagonal group is going to be generated by these permutations. So first of all, so the underlying set, as I said, is G to the k. So we will be acting on this set. I mean, first of all, the group G to the k, the direct product G to the k is acting on this set by right multiplication. So this is going to induce permutations. So these are going to be one group of, or one set of permutations that will make part of our generating set. And now another copy of G is acting simultaneously on this set by left multiplication. So if I take an element, little g, from my group G, and I take a point from G to the k, so I can left multiply the entries of this point by little g. on the left. So this is acting by left multiplication simultaneously on the entries. I can also take an automorphism of G. So the underlying set is G to the K. And when I have an automorphism alpha, so I can have alpha act on G to the K simultaneously on the K coordinates, right? So this is also going to induce permutations of omega. So I have the group SK, so the symmetric group. To be G to the K, and SK, the symmetric group, permutes the entries in an element of omega, and this is going to induce permutation. So this is another ingredient in my group. And finally, we have this permutation that we call tau. So what tau does is it takes a K tuple, G1 up to GK, to this other K tuple. So this is G1 inverse, comma, G1 inverse times G2, G1 inverse times GK. So this is might be a bit weird, but this is what tau does. And the diagonal group that we are going to denote by DG, comma, K. So the diagonal group is the subgroup of the symmetric group on this set omega generated by all these permutations. So this is a bit mysterious. I have a bunch of permutations, and I say that they generate some sort of group. So this is the diagonal group. So of course, I mean, this is not very useful unless we know some structure. So as an abstract group, the diagonal group is isomorphic to this group that I wrote down here. So the diagonal group is isomorphic to like a direct product of K plus 1 copies of G, quotiented out, the center being quotiented out, and extended by this direct product of the outer automorphism group, direct product with the symmetric group of degree K plus 1. So what's happening here is that this G to the K, so this corresponds to this G to the K acting by right multiplication, right? So this lonely G corresponds to G acting by left multiplication. But you see, when you have an element in the center, so if you consider a central element in G, so that sort of acts by left multiplication, its action is going to be the same as its action by right multiplication. So this is why you have to sort of quotient out this center. And then in the ingredients, I had automorphisms of G, but inner automorphisms would be already contained in this G to the K plus 1, because inner automorphism you can obtain by left multiplication and then by right multiplication. So you only need to worry about, you only need to add outer automorphisms. And this SK plus 1, so that kind of arises as the group generated by SK and tau. So this is why this tau is necessary, because we have, so we need a permutation group on SK, on K plus 1 letters. So we will get a permutation group on K plus 1 letters, right? And so this is the abstract structure of this group. This is abstract structure, and so its order, for instance, you can calculate its order whenever G is finite. Of course, if G is infinite, it's going to be an infinite group. When G is finite, you can get, its order is going to be the order of G to the K times the order of the automorphism group of G times K plus 1 factorial. And so we are often interested when this group, when a permutation group is primitive. So in the theory of permutation groups, we are interested in primitive permutation groups. So primitive permutation groups are the permutation groups which do not preserve any non-trivial partition of the underlying set, and they are transitive, of course. So this group is going to be transitive. So this is the first observation, because this G to the K is already going to be transitive. And primitive means it doesn't preserve non-trivial partition. underlying set, and you can characterize when this group is primitive. So it's gonna be primitive if and only if the starting group G is characteristically simple, and if G is an elementary abelian P group, then the prime P does not divide K plus 1. So this result holds for finite groups and for infinite groups. So we get exactly when this group is primitive, and so we are, as I said, okay. So why it's not very strong justification to justify why we are interested in this group. To say that it might be primitive. The reason why we are interested in this group really is that because such groups occur as maximal subgroups, again, as symmetric and alternating groups. So this is the theorem. So this is not our theorem. So this theorem is known. So let me put it here. As I said, so whenever I don't attribute a theorem to someone, it would be ours, but this is not ours. So this was known before. That if G is a non-abelian finite simple group, then this diagonal group is going to be a maximal subgroup of either the symmetric group or the alternating group. And this, as I said, I mean, this occurs. So the fact that such maximal subgroups exist occurs in the Onnan-Scott theorem, and it was later proved by Prager, Saxel, and Liebeck that these groups are maximal always whenever G is a finite simple group, and it's not going to be maximal if G is not a finite simple group. And so this theorem, and this is what really prompted our research in this direction about diagonal groups, because we were interested in combinatorial structures that can be preserved by this diagonal group. So in fact, we were interested in some sort of combinatorial or geometric structure such that the diagonal group would be the full automorphism group of this combinatorial structure. So you see, this is because for the other types of maximal subgroups of symmetric and alternating groups, the other types of maximal subgroups are full stabilizers of combinatorial or geometric structures. And this maximal subgroup was always described as something that, okay, so take a finite simple group G and do this, and you get a maximal subgroup. And we were interested, so can it be described as the automorphism group of something combinatorial? And in fact, so one answer to this result is given by the following theorem, that this diagonal group is in fact going to be the full automorphism group of the diagonal graph. So this is the first part of this theorem, that unless the size of G is very small and the number K is also very small, so here we have the explicit exceptions. So if G is a group of size 2 and the number K is 2 or 3, of G is a group of size 3 or 4, and K is equal to 2, then this is not true. But otherwise, the full automorphism group, the automorphism group of the diagonal graph would be equal the diagonal group. So this is one geometric structure that is preserved by this diagonal group. And another interesting fact that also occurs in this paper is that the isomorphism type of the diagonal graph determines the number K and the isomorphism type of G. So you see, if you take like G to be a finite group, so you can take two finite groups which are not isomorphic and the same number K, or numbers, different numbers K. So you can take two finite groups which are not isomorphic. But if you do take the same number K, then you get a graph, you get two graphs which have the same number of vertices, the same number of edges, the same valency. It has the same, sort of lots of the same graph theoretic properties. But our result says that these graphs are not isomorphic. So these diagonal graphs are isomorphic not isomorphic unless you take isomorphic groups and the same number K. So this is interesting that you can get like a like if you take finite groups, you can take a set of graphs with very similar properties, but they are not isomorphic. And also, this is a more recent, even more recent result by Rosemary Bailey and Peter Cameron, that even though these graphs are non-isomorphic, if you take two non-isomorphic groups, the spectral properties of these graphs are independent of the group G. They only depend on the size of G. So if you take two groups of the same size and the number k, then you construct these two diagonal graphs. So the diagonal graphs will have the same eigenvalues and the same multiplicities, the same dimensions for the eigenspaces, which is quite interesting. It doesn't depend, even though the graphs are non-isomorphic, these data don't depend on the group, they only depend on the size of the group. Okay, so this is one combinatorial structure. So the other thing I wanted to talk about is these partition lattices. And so the partition lattices give us another characterization, another combinatorial structure to construct that is left invariant by diagonal groups. So whenever you have a set omega, so you can consider the set of partitions of omega, and the set of partitions of omega form a lattice under the operations of join and meet. So whenever you have two partitions, you can ask whether one partition is finer than the other partition, or one partition is coarser than the other partition, and it gives you some sort of partial ordering on partitions. All right, and the join is essentially the supremum of two partitions, and the meet is the infimum of two partitions under this partial order. And with these two operations, you get a lattice. So this is called the partition lattice of the set. And of course, you can consider sublattices. So a partition lattice would be something which is closed, a set of partitions which is closed under these two operations. And we also assume that the partition lattice contains the trivial partition into singletons, and also the universal partition, which contains only one block. And so one example, one trivial example is that, you can consider partition P on the set omega, and the partition lattice generated by a single partition would contain three partitions. I mean, you could consider a trivial partition, but assume this partition is non-trivial. So in this case, you would get precisely three partitions in the partition lattice generated by this partition. So you would get the partition that we denote by E. So this is the partition into singletons. So you get the partition P, which you took, and you get the universal partition in which you have only one block. So this is a trivial partition lattice. So another example of a partition lattice that I'm gonna use later is consider a vector space. So whenever you have a subspace, you can consider the partition of the vector space into the cosets of the subspace. And so you can take you can take all the subspaces. You can take the set of subspaces, and you consider all the partitions with respect to these subspaces, and it's going to be a partition lattice. So it's actually going to be isomorphic to the lattice of subspaces. And so this is one of what we are going to call later affine partition lattice. So the affine lattice. So this is what I'm going to refer to as affine lattice later. So another example related to the Hamming graph of a partition lattice. So consider omega. Now consider omega to be the kth Cartesian power of a set delta. So delta is a set, so delta to the k is the kth Cartesian power. And for each I, which is a subset of numbers from 1 up to k, define an equivalence relation on k tuples. Define this equivalence relation on k tuples such that two k tuples would be equivalent if and only if the entries alpha I and beta I are equal whenever the index I belongs to this subset, right? And you can consider the set of these partitions. So you get a partition for each subset. You can take the set of these partitions for every subset of 1 up to k, and this is going to be the set of these partitions is going to be a partition lattice. So here I'm identifying partitions with equivalence relations. So I get a partition lattice, and this is what we call a Cartesian lattice of partitions. So this is what we call a Cartesian lattice of partitions, or Cartesian partition lattice. And here, so why is it related to the Hamming graph? So here, the minimal partitions of this partition lattice are formed by the type I, or are related or determined by these type I edges of the Hamming graph. So type I edge, so type 1 edge would be something between two vertices that are different in the first position, and they are equal in the other position. So this would be a type 1 edge. And so the blocks of the minimal partitions are in fact the maximal cliques of this Hamming graph. So this partition lattice is very much related to the Hamming graph. So the minimal partitions essentially determine the Hamming graph and are determined by the Hamming graph. And the maximal partitions are the partitions that we that form the so-called Cartesian decomposition. So the Cartesian decomposition, so just to remind that the Cartesian decomposition of a set is a set of partitions such that whenever you take a block from each of the partitions, then the intersection of these blocks contains precisely one element. So the Cartesian decomposition kind of determines the decomposition of the set into Cartesian product. How much time do I still have, Christina?
Csaba, you still have at least 10 minutes, but even some minutes more because you are the last speaker, so don't worry.
I don't want to take people's time unnecessarily. What did you say? So I have still
10 minutes. You have, yeah.
How many? 10?
10, yes.
10 minutes, okay. So this Cartesian lattice, this Cartesian lattice is determined by its minimal partitions, and it's also determined by its maximal partitions. So this is what this proposition says, that whenever I have some sort of Cartesian decomposition in a set omega, so the set of partitions that satisfies this property, then I can consider the Cartesian lattice, I can consider the partition lattice generated by these partitions, and then I can consider the minimal partitions in this partition lattice generated by the Cartesian decomposition, and these minimal partitions will correspond to the edge set of a Hamming graph. So in some sense, so these Cartesian decompositions and Hamming graphs are equivalent objects. So they are sort of Cartesian decompositions are maximal partitions. Hamming graphs are minimal partitions of some sort of Cartesian lattice. And so we can do the same with the diagonal graph. So in the case of diagonal graph, we get something that we call the diagonal semi-lattice of partitions. So it can be constructed the following way. So suppose that gamma gk is the diagonal graph. So remember this thing that we obtained from the Hamming graph, and then we can introduce this equivalence relation on the set of edges, on the set of vertices. So two vertices are going to be equivalent under this relation that I denoted by equivalence I. So I have several equivalence relations. So for each I between 0 and k, I will have an equivalence relation on the vertices. So two vertices going to be equivalent under this relation if and only if they form an edge, an I edge. in the diagonal graph. So you remember in the diagonal graph, I was talking about type 0 edges, type 1 edge, type k edge, etc. And this gives an equivalence relation on the vertex set of this graph. And I can consider the partition lattice generated by, so Li is the partition lattice generated by these partitions that correspond to this equivalence relation for each j except j equals I. So I get here I get k plus 1 partitions, and I can consider the partition lattices generated by k of these k plus 1 partitions. And this is going to be a partition lattice on the set omega, which is g to the k. And the lemma says that this partition lattice is going to be a Cartesian lattice for each I. So I get, so from this diagonal graph, I get k plus 1 lattices. I get k plus 1 partition lattices, and each of these lattices is going to be some sort of Cartesian lattice. And what's interesting is that the union of these lattices, so I can take the union of these Cartesian lattices, and it's not going to be a partition lattice because it's not closed under the meet operation, but it's closed under the join operation. So this is what we call a join semilattice. It's not joined, it's join. So this is what we call a join semilattice. So the union of these Cartesian lattices is going to be closed under the join operation in the partition lattice. So this is what we call a join semilattice. And this union is what's called a diagonal semilattice associated to the group G and to the number K. So whenever you get a group G and a number K, so you can consider this semilattice of partitions. This is determined by this data. And this is what's called the diagonal semilattice. And so let me just show you these two theorems to close. I think I'm running out of time. Just these two results so this is a construction. This is an explicit construction for a diagonal semilattice. And one can ask whether it's possible to axiomatically characterize these diagonal semilattices. So what we were after in this research was some sort of axiomatic characterization that didn't require a group to start with. So we wanted some sort of result which says that if you have such lattice or such a set of partitions, then there will be an underlying group. And this group will determine a diagonal graph, and it will also determine a diagonal group. And this is what this result says, that so supposing you have k plus 1 partitions of a set, any set, such that any k of these k plus 1 partitions generate a Cartesian lattice. So considering any k partitions, they generate a Cartesian lattice. And these k partitions are the minimal partitions in this Cartesian lattice. Then the joint semilattice generated by these partitions is a diagonal semilattice corresponding to some sort of group and some number, k at least 2. So this concept of diagonal semilattice can be defined using a completely axiomatic approach without starting with a group, and if you have such a structure, so this group will emerge from this data, and one more theorem that another thing such that the full diagonal group is the automorphism group of the structure is this diagonal semilattice. So this theorem says that the full automorphism group of the diagonal semilattice is in fact equal to the diagonal group. So now we have two things such that the diagonal group is the automorphism group of these structures, the diagonal graph and this diagonal semi-lattice. And I think I will stop here.
Thank you, Csaba, for very nice talk. So let's just give a round of applause for Csaba.